Good morning, everybody. Good morning. It's awesome. So we're gonna let a couple more people sign in and then we're gonna go ahead and start. All right, but thanks guys for coming and joining on. Got some cool stuff for you today. I have some fun experiments I think you guys are gonna like. So we'll just go ahead and give people 1 minute to log in and then we'll go ahead and start, okay? I hope I'm outside. I hope I don't get rained on, but I think I should be okay. The forecast is a little cloudy, so we'll see. Okay, we're gonna give people 1 more minute and then I might go ahead and start presenting, okay? So hang tight, guys.
It says it's cloudy.
It said it's cloudy, you're right. It said it's cloudy, but I don't see any rain clouds necessarily. It just kind of looks like cloudy. So hopefully, if I feel some rain, I'll put up my umbrella. I'll take a little break and put up the umbrella, but I think it should be fine. We'll be good. All right, I'm gonna give it 1 more minute and then I'm gonna go ahead and start, all right? And then people can join in when they come in. Hope you guys are enjoying your summer before we go back to school, however that may look, but summer is fun. It's nice to just chill. All right, cool. We got a couple more people. So I'm gonna go ahead and start and then people might join in later. But for those of you guys that are new to Ava Summer Science, welcome. Basically how this goes is I take a question that somebody submitted this week or the weeks prior and I answer it, and then we also do some experiments to try to figure out what's going on. So we're gonna take a look at a question today that I got that I thought was kind of interesting, and we'll see if we can answer it, okay? So I'm going to switch screens, so I'm presenting to you guys now, and then we'll go ahead and take a look at the question for this week. So I'm going to start presenting. So the question I got this week was, why do roads crack in the cold and buckle in the heat? Okay, so if you think in Chicago, we get this a lot, especially with the cold, because we're cold here a lot. You see that the roads have like cracks in them or like little patches that they're all cracked or broken up or potholes. And why does that happen, right? Because if you go somewhere warmer, you're not gonna see you're not gonna see that as much. So we're gonna go ahead and take a look at that today, and it has to do with water, which funny if it rains today, hopefully not.
I think I know the answer.
You do? Okay, I'm gonna have you hold on because there's some people that they don't know yet. I might go ahead and tell them and then you can help me out, okay? Sound good?
Yeah.
All right, perfect. So we're gonna go ahead and we're gonna start by talking about what is water, okay? So water is a compound that's made up of 2 hydrogen atoms and 1 oxygen atom. And for those of you guys that were with me last week, remember what atoms are. Atoms are the except particle of anything that we have in the universe. So if we break things down,
except for quarks.
Except for, yeah, you're right. So so that is what water is. Basically, it's made up of 2 atoms of hydrogen and 1 atom of oxygen. Okay, so we're getting super duper small particles that we're putting them together, and that makes up water. Water is actually considered an inorganic compound, which is kind of weird. So when we think organic, inorganic, it's called inorganic because it was not created by a living organism. No living organism produces water. It just is here. So it's not considered. Guys, if whoever's writing, please don't write on the screen. Thank you. You can erase that. Thank you. So that's what water is. Water molecules, and we call these H2O. Now you understand why it's called H2O, because you have 2 hydrogen atoms and 1 oxygen atom. They connect together, right? Each little water molecule connects together through hydrogen bonds, okay? Which basically means that the oxygen atom of 1 water molecule is going to bind to the hydrogen atom of another molecule. they are attracted to each other, and it has to do with their charges. But all you really need to know is that oxygen binds to the hydrogen, they bind together, and then we could get a chain of water molecules. So it's not just like, oh, you know, every single like drop of water is one water molecule. It's thousands upon thousands of water molecules that are connected together through these hydrogen bonds, okay? So now let's talk about why is water important? Like what purpose does it serve? So water covers 70% of Earth's surfaces, and living organisms are made up of mostly water. The human body is made up of 60% water. So water is really important to us. But this is a picture I included, and this is what the Earth would look like if there was no water on it. And you can see how dry and like, it just looks like bad. That's because there is no water, and water is necessary for all walks of life. So without water, this is what we look like. Another thing that water does is it helps to dissolve any nutrients we have in our blood so that our cells can use them to help our body function. Water also helps with regulation of our body temperature, okay? So way to think about this is like when you're running, if you're running a mile or something and you start overheating, right? Your body is getting warmer because it's like you're using it and your muscles are pumping. When your body is overheating, the temperature, there's a little mechanism in your brain that regulates your body temperature. It says, hey, you're too hot right now because you're running and you're just overheating. So what it does is it will have us release water as sweat. And when that sweat dries up, it helps to cool our body. That's the purpose of sweat. It's water that's released from our body that when it dries up, it kind of cools us down. So water helps us with that. Another thing too is water surrounds our spinal cord and like our joints, so like your knee joints, your elbow joints, to protect you against injury. They kind of makes like a cushiony little pillow for us so that we don't hurt ourselves.
Excuse me?
Yeah.
Is it okay if I send you the answer to the question of the day in the chat?
I want you to hold off on that, okay? Because I just don't want to make sure that everyone gets a chance to kind of learn about it, all right? If you don't mind. I'll leave some time though for questions at the end, okay? If you have a question or something like that, if you have a comment. So, so now we're gonna go on to the next slide here, and we're gonna take a look at what are the states of water. And a lot of people are like, well, this seems really obvious what the states of water are, but there's a lot going on behind it, and there's a lot of science behind it. So water can be found as a solid, ice. It can be found as a liquid, water, and it can also be found as a gas. And we call this water vapor. And water vapor, we see that in steam, we see that in clouds. That's water vapor. It's not like actually, you can't like actually touch it and hold it, but it's like this gas. So now when we have these phases, right, to transition between them, those transition states those transition states have names as well. So when you're moving from a solid to a liquid, we call it freezing. Backtrack. We go from a solid to a liquid, it's called melting. You're melting water. Now, when we go from a liquid to a gas, it's called evaporation or vaporization. I actually use the word vaporization because evaporation, I'll talk about evaporation a little bit, but water to liquid to a gas is going to be vaporization. We go from a gas to a liquid, it's called condensation. We go from a liquid to a solid, it's called freezing. So I'm sure you guys are most familiar probably with melting and freezing because you've seen that happen before. But maybe condensation and vaporization and evaporation you're kind of confused about. So water goes from a liquid to a solid at 0 degrees Celsius or 32 degrees Fahrenheit. And then it goes from a liquid to a gas at 100 degrees Celsius or 212 degrees Fahrenheit. And the reason that we use kind of Celsius first is just because it's more standard. Most of the world uses Celsius except for the US. But basically those are the temperatures, 0 degrees Celsius and 100 degrees Celsius to change phases. So here, now this is one phase I want to talk about. When we go from water to a gas, so water to steam, it's called vaporization. And that happens when you see like a raindrops and there's a big rainstorm and you see the raindrops and they kind of dry up. That is vaporization. But what actually is happening, there's vaporization, there's something called evaporation. And evaporation is basically when you have a droplet of water and you're skimming off the top and you're letting that top part dry. So imagine you have a little raindrop that's sitting there. If we dry off just the top, that's called evaporation. Now vaporization is a little bit different. Vaporization is instantly the whole drop magically disappears. And realistically, that doesn't happen because we never get hot enough to have that happen. So what we do have is evaporation. And evaporation is you're just skimming off the top of the droplet. That's all we can really dry up. We can't dry up the whole thing, but just the top. And eventually, as you keep getting rid of the top, we get rid of the water droplet. So evaporation kind of works a little bit slower, but it is a way to have us turn water into steam. And then condensation, a great example of condensation is on a hot day, if you have like a glass of lemonade, and you know it's super hot, maybe you have ice in your lemonade or whatever, and you see those little beads of water that form on the outside of the glass, right? Why is that happening? Well, that's called condensation, because water vapor, there's tons and tons of water vapor in the air. And when water vapor or hot water vapor in the air comes into contact with your cold drink, it starts to change form and go this way. It starts to go the cooling route, and it turns into a liquid, little liquid droplet. So I hope that kind of helps. So you guys, is when you're adding heat to water, because I'm talking about this hot glass, or I'm talking about, sorry, the hot air and the cool glass. And when the hot air touches the cool glass, we change states. Adding heat to water makes it move from a solid to a liquid and to a gas, okay? So when we're adding heat to water, we're able to go through these phase changes. And the reason why is, guys, the water molecules, as we start adding heat, the water molecules start moving faster and faster and faster, and they start getting less rigid and they start bouncing off of each other. And that's what the heat is doing to us. So it's helping us change states. So if we look over here, this is what water looks like as a solid, okay? It has a really rigid structure, this kind of diamondy structure. And there's water molecules here, but they're really like kind of tightly, they're in a weird like formation. Now, once we add heat and we move into a liquid water, right, we're able to break away from this tough structure because we're adding heat and we're letting the particles move around more and bounce around more. Okay. So here we go now, the particles are bouncing around, they're knocking into each other, that's liquid water. And then when we get to a gas, guys, the gas has more space to expand. So these particles are still bouncing off of each other, but they just have more room to do so. Where here, they're a little bit more tightly packed and they're bouncing around off each other. But the main idea, guys, is that heat, when we're adding heat, we're allowing the particles to bounce around more. So this, add heat, we're letting them bounce around. We add more heat, they're bouncing around even more, except that they have more space. Okay, so I hope that kind of makes sense. Okay, so now we're gonna go ahead and talk about what are the properties of water, okay? So water is the most dense as a liquid, medium dense as a solid, and least dense as a gas. And I'm sure you're like, whoa, Ava, slow down, what is density? So density, when I talk about density, I'm saying how many water molecules can I pack into a space? And since water is a solid, this is what water looks like as a solid, right? It has this like crystalline structure, we call it, where if you really like to zoom in on the water molecules, you see that they're arranged, they're kind of like spaced out from each other, almost like social distancing, guys. I kind of think about this like social distancing. Water molecules are social distancing from each other here. So they can't pack as many water molecules in this space. But in a liquid, right? Liquid, no social distancing, everybody can come to this party. And you see, guys, all these water molecules are all on top of each other, they're bouncing off of each other, and we could pack more water molecules into a liquid space than we can into a solid space. So that, and then when we have a gas, guys, please don't write on the board, thank you. And then when we have a gas, right, you can also pack in a lot of water molecules, but they are free to spread out as much as they want to. So they're not as dense, okay? We're not just looking at this one area. We're looking at those water molecules can spread out as much as they want because they're a gas. So the main idea here, guys, is that this is why ice floats in water, because ice is less dense. There are less water molecules in this space than there are in this space. There's less water molecules in a solid than in a liquid. Liquid water is more dense than solid water. So really interesting though, guys, for you guys to see the structure here. These are all spaced out, they're socially distanced, so you can't fit as many in the space, but with a liquid, they can bounce into each other, they're all on top of each other. It is so many water molecules all together. It's very dense, we call it. So another thing about water, water has a property, it's called surface tension, and maybe you've seen this before, but basically what it means is that those water molecules, remember how I was talking about the hydrogen bonds between water molecules? Those hydrogen bonds are not super strong, but when you have thousands upon millions of water molecules and they're all hydrogen bonded, they actually can be kind of strong, right? When we have tons of them, there's strength in numbers. So basically, when we have tons of water molecules and we pack them together, like you do in a liquid form here, like liquid, they end up being really tight and they resist being stretched. So this is what allows like bugs to walk on liquid water. It's because of surface tension. It's because the water molecules, they become tight and they resist breaking apart because those hydrogen bonds, there's so many of them, and together they're really strong and they don't want to break. So even though I'm trying to break them apart, they don't want to break because they're bonded together. So that's why you can actually have some light creatures walking along water. Of course, can we walk on water? No. But if you're a light creature like that, you can because of surface tension. And the last thing is water is both cohesive and adhesive. So cohesive, what that means is that water molecules can stick to water molecules, and that's through hydrogen bonds. But also too, guys, water molecules can stick to other kinds of molecules. You've seen water on plants, you see water on the ground. Water is able to stick to a variety of substances, but it also, water molecules stick to themselves, okay? So this is kind of cool. Okay, so now what we're gonna talk about is why do roads crack in the cold, okay? So you've probably seen something like this. You guys all live in Chicago. You've probably seen something like this, right? Where you have a cracked road, it's snowy, it's icy, your parents are probably driving around it. So the reason that this is all going on, so concrete, so when you think of concrete, it's like what makes your sidewalks, and asphalt is what makes our streets, they are called porous, which means that they have tiny, tiny holes in them that make them permeable to water, which means that those little holes allow them to absorb in water, okay? So it's like you have concrete, and it has a couple little holes in it, it'll take in any water that falls on it. So when we have heavy rainfall, guys, or we have melting snow, which is water, the roads and the sidewalks, they end up absorbing that water through those little holes in the concrete or the asphalt. They kind of absorb it. So when it's cold out, right, that liquid water that they absorbed, even though they absorbed it as a liquid, guys, now it's going to start to freeze. It's going to turn into a solid. And when it freezes, that liquid water is actually going to end up expanding. And the way I like to think about it is like this. Here's like, I'm imagining these are like little marbles, okay? Maybe we have, I don't know, 30 marbles here. And those 30 marbles are all packed together. I can fit them in the palm of my hand. I can squish them all together. But now I'm saying, hey, you're going to become a solid. So you have to fit into this strict form. Okay, so now I have to put those marbles, those 30 marbles, in slots, and they have to socially distance from each other. I'm using socially distance because it actually fits pretty perfectly here. But now we have to take those marbles, those 30 marbles, and we have to say, hey, guys have to space out. And guess what? If we space them out, guys, they're going to take up more room than they did before. You guys see that this shape right here is, this shape right here is a lot smaller than this shape, just because we have to space out those particles. So when we freeze water, guys, we're spacing out the particles, so that amount of water is going to expand. So when that expands, guys, and that water is freezing up, it's expanding in the road, it's causing cracks because it's pushing on the asphalt, it's pushing on the road. So that when water freezes and expands, it puts pressure on the road and it causes it to crack, okay? So it has to do, guys, with we're taking in liquid water. When it gets cold out, like in Chicago, it's gonna freeze up and it's gonna expand because remember the forms of water, liquid water, we can pack it together, but solid water has to be socially distanced, it has to be spaced out, and it's gonna take up more room. And it's not like we can just get rid of water molecules, right? If this is what we came in with, we have to come out with the same amount. So we just have to space them out, okay? So now, guys, we're going to go ahead and take a look at why do roads buckle in the heat, okay? So now we kind of talked a little bit about we talked about how roads in the summer, roads in the winter, how they crack. Now we're going to talk about in the heat, guys. We don't really see this too much, but they have this problem in a lot of like really hot places. Like you can think like Arizona and California, but you see that the roads are actually coming up and they come up like a peak and they buckle. And this guy's kind of looking under because it's like the road pops up. So just like I said before, right, we know concrete and asphalt, they have these little holes and they're able to take in some water. So when it gets really hot, guys, they take in water. And remember, if we have liquid water and we're heating it up, it's going to turn into a gas, okay? So that liquid water ends up turning into a gas. It turns into water vapor. Now that the water is into a gas, guys, it's expanded. Remember, liquid water takes up less space than a gas. The gas is going to take up as much space as it wants because it's a gas, and those water molecules are going to be so spread out. So the same amount of liquid water molecules that we came in with, guys, they are now going to spread out as we turn it into a gas. They're going to kind of expand. And when that happens, guys, they start pushing the roadway up. So when we have liquid water here and it gets really hot, that liquid water is going to start to vaporize and evaporate. And you see that those water molecules now are going to turn to a gas and kind of spread out and spread their arms. And they end up pushing the roadway up. And a lot of times this happens too, where you have a crack, maybe you have a crack from the winter, but then it's really hot. And then that liquid water that's now turned into a gas, it actually ends up pushing that crack apart and up. So it kind of like, it's like almost like a gas is rising up out of the ground. So that's kind of the best way to think about it. So when we're buckling, guys, same thing, we're absorbing water, except this time now, because it's hot, we're turning it from liquid water into gas water, and that gas expands and it causes the road to buckle. So I hope that kind of makes some sense now as to why we crack and why we buckle in different weather temperatures. So something, guys, I want you to think about for tonight, I always like giving you guys a question to think about with your family and friends, because being a scientist, the most important thing is that you're able to talk to people and you're able to communicate your ideas. Super duper important, and kind of share what you think. So the question that I want you guys to think about today is, what is the best solution for road buckling and for road cracking? And you might say, okay, maybe I'll get rid of all holes in the road, or make all asphalt and concrete. We're not going to put any holes in it. They can't absorb any water. But what about flooding, right? We have flooding problems. And if our roads can't absorb any water, that's a problem too, because then we're going to have worse flooding. The roads do help with flooding because they absorb some of that water, but then they crack. So kind of start thinking about maybe what's the solution to road buckling and cracking. If you have a solution, you can email me and I'll kind of discuss it with you. So that was our lesson for today. And now we're going to kind of move into our experiment, okay? So I'm going to exit. I'm going to stop my screen share. And I'm going to now move. Here you are. Okay, cool. Now you guys can see me. If you have your video on, can you guys please turn it off? Just because when we have experiments, it's really hard for everyone to watch. It just, I don't know, sometimes it goofs up. So now I'm going to do our experiment today. And our first experiment, it has to do with a penny and water. Okay, so I'm going to try to position this so you guys can see it. So this is just a glass, guys, just a normal glass. But I'm just going to use it to put my penny on top. This is just a normal penny. This is not a trick penny. Completely normal penny. And there you go. You guys can see it now. Okay, you guys see the penny on there? Yeah. Okay, cool. So we have just a normal plain old penny on my glass. So now what I also have here today is a dropper. Let me see, put it in the camera. This is just a dropper. And what this is used for, you guys will see this maybe used if you're like making drops of, or if you're doing like drops of candy or drops, anytime you have droplets of something, we use a dropper just because it makes it super easy to work with. So I have a dropper here, and what I'm going to do, guys, is I'm going to take, I have some water here, and my water is very, very blue. I dyed it blue just so you guys could see it better on the penny, because I know this camera can be kind of tough. And put some water droplets. Hey guys, can you guys turn on mute, please? Thank you. I'm gonna go ahead and put some water droplets on top of the penny, and we're gonna see how many water droplets we can fit on top of the penny. I think you'll be really surprised by the answer. So here we go. I'm gonna start putting water droplets on the penny. Let me see here. Okay. So here we go. Here's one. Now I'm gonna do two. Now I'm gonna do three. Now I'm gonna do four. 5, 6, 7, 8, 9. Okay, there we go. We got 9, guys. And if you guys can see it, it's like forming like a little bubble. Do you guys see that little bubble it's making? Which is super interesting. We're gonna talk about why it's doing that. Because I know what you're thinking. You're thinking, Ava, isn't the water going to go everywhere if you keep on adding water droplets? But we're going to see how many water droplets we can fit on this penny and let them bubble, okay? We're going to talk about why it's not just totally falling over and spilling. Okay, so here we go. Here's drop 11, 12, 13, 14, 15, 16, 17, 18. Okay, So we got to 18 water droplets, guys. And now you can see that it's kind of spilled. You see how there's like a puddle over here? The water now spilled. But I was able to fit, guys, think about that for a second. I was able to fit 18 water droplets, 18 drops of water on the penny, and it started forming this bubble. What was actually happening is, guys, that is the property of surface tension that I was talking about, is that water, when we have tons of water molecules in each drop of water, it's going to resist breaking apart. So those water molecules are like, hey, Ava, even though you're adding more droplets, we're not going to break apart. And we're going to keep on forming this like bubble. We're going to form this like film so that we don't break apart, guys.
That reminds me of something.
Really?
When I was flinging water onto my fire thing, there was a ring around it, and the water created this weird marble thing that was spinning around the ring.
Super duper cool. Yes, that is what we see. That is what we have. We are ending up with surface tension there, guys. So that is what I want to show you, is that is surface tension. You see that I'm adding water droplets and they don't want to break apart. That's why I could fit 18 water droplets on a little penny. Think about how small a penny is. I was able to fit 18 water droplets because they formed a bubble and they were resisting breaking apart. So super cool. Now I have one more other experiment for you guys. And this one involves some hot water and some cold water. And I'm doing this experiment and I want you guys to watch it, but please do be careful when you're doing this at home if you are going to do it, because hot water is really hot and it can burn you, and I don't want any accidents. So please do this with parent supervision if you do it. So I have 2 glasses of water here, 2 glasses of water, and I'm going to fill 1 glass of water with some ice cold water, okay? This is my ice cold water. I filled some ice cold water before I started my presentation, and I'm going to go ahead and fill, I'm going to make sure you guys can see this. Yeah, there. Okay, so I have some ice cold, and don't worry about the black labels, guys, in the glass. That shouldn't have an effect on anything. So I'm gonna pour some ice cold water into 1 glass, and you guys maybe will see the ice coming out. Ice cold water. Okay, you guys can see I have ice cubes in the water. It's ice cold, cold to the touch. Okay, so that's my ice cold water. Now in my other glass, guys, I have really, really, really hot water, okay? I boiled this water on the stove. That's why I want you guys, if you do this, make sure you have parent supervision. But here I have some super duper hot water, okay? So I'm gonna pour that, and it's actually steaming because it's so hot. Okay, so here we go. I have hot water in here. And I'm filling it, guys, the same amount. There's no difference. Now I have my super duper hot, very, very hot water. So now what I'm gonna do, okay, and maybe, I hope, yeah, you guys can see the glasses. I think they're in view there. So now what I'm going to do, guys, is I'm going to put food coloring in each glass of water. And I'm going to put red food coloring because I think you guys can see it best. I'm going to put a drop of red food coloring in each glass of water, and we're going to go ahead and take a look and see what happens, okay? Hey, guys, can you turn off your video, whoever has their video on, please? Because it's hard to see the experiment. Thank you so much. Okay, so we're going to go ahead and see now what happens when I put food coloring in the water, okay? So just hold off, no video, guys, no audio, just so this will work out well and everyone can see it. So I have some food coloring here, and I'm gonna start by putting my food coloring, my red food coloring in the cold water, and we're gonna see how it kind of takes to it. So here we go. And now I'm gonna put my food coloring in the hot water. We're just gonna kind of let this sit and let it kind of do its thing. And hopefully you guys kind of see what's happening already. This glass, this is the cold water glass. It has food coloring in it, just to let everyone know. It does have food coloring.
Diffusion takes place more easily in hot temperatures than cold.
Yeah, we're going to talk a little bit about why that's happening, for sure. So just keep your eyes, guys, on this and see and look at how interesting this is. So you see, in this glass, I'm actually turning it a little bit so you can see it. But basically what's happening is, you see there's like streaks of red that are kind of coming down. We see a little bit of red there, and hopefully, let me make sure you guys can see this. But you see a little bit of red. I'm gonna hold this glass up to the camera. You see it, this is my cold water glass. You guys see there's a little bit of red that's coming down, but it's kind of like streaky. There isn't that much red. Whereas in my hot water glass, guys, this whole thing is red. Whole glass is red. You see there's totally red. So if we're going to talk about now why is this happening, the reason is, remember I said that hot water molecules are moving faster. And that's why when we go from a solid, right, we have the super duper rigid structure in a solid, And then a liquid, we're warming up those water molecules so they can bounce into each other. Same thing is happening here, guys. In my cold water glass, the water molecules are not moving as fast, so they can't really move around that food coloring. But in my hot water glass, guys, those water molecules are having a party. The water molecules are bouncing around everywhere, and they're taking that food coloring and they're just bouncing it around everywhere. But in my cold water glass, guys, it's colder. The water molecules aren't moving around as much. It's closer to a solid, and they are not moving around as much. And that is why we're seeing that it's not moving as fast and it's not working as well. So hopefully that makes sense, guys, as to why hot water, when I talk about hot water and liquid water, that all those liquid water molecules are moving around. Now you see it in action. That's why they're carrying that food coloring. Whereas with this one, our water molecules are not moving as fast, so they can't carry the food coloring as well. You know, they can't drag it as well. So thank you guys for watching today. I'm gonna take 2 questions. We have time for 2 questions. So if you have a question, please unmute yourself and go ahead and ask it.
I have a question.
Yeah, go ahead. Yep, we can hear you. Mhm.
Why is so ineffective in hard water?
One more time, can you repeat that?
I have a different.
Yeah, what was your question? Sorry, I couldn't hear you.
Heat? What is specific heat?
What is specific heat? Is that what you were asking?
Yes.
Yeah, so specific heat, that's a good question. So we're talking about specific heat. That is the heat that we need water to be to change forms, okay? That's what we call specific heat. It's like a temperature. It's a specific temperature that we need, that when we talk about water, we talk about oil, everything has a different like specific heat temperature that's needed to change forms. Do we have any other questions? Hopefully that answered your question.
Yeah, that did
That's
answer
it?
my
Okay,
question.
good. Yeah, so it's
And I know that the specific heat of water is very high.
Right, exactly.
Which
so that
is
the heat.
why it proves to be useful in hot water.
Exactly, and that's why, if you remember me saying, I said you have to be super duper high. You have to be 100 degrees Celsius, which is 212 degrees Fahrenheit, to change from a liquid water to a gas water. That's the specific heat of water. That's the heat that we need. Has to be to change forms. Okay, so I hope that answers your question. Basically, it's the temperature that we need to get water to change forms. And water is a really high specific heat because we're always breaking. We're going from a super duper rigid and crystalline structure to a liquid structure to a gas structure. So we're always changing forms. There's a lot of the molecules move very differently, so that's a high specific heat. We need a lot of heat to change forms. Okay. Any other questions, guys? Any other questions? I have time for one more question. Do you have a question? Zachary is awesome.
No.
No? Okay. All right, last call for questions, guys, before we end everything. Anything? Any questions? All right. Well, thank you everybody for coming to today's meeting. I really appreciate that you guys all came and you watched. I hope you learned something more about water and why our roads crack and why our roads buckle too. So I hope that makes sense. Zachary, do you have a question, or are you, sorry, you're on mute right now. You have a question? Yeah, mute, you didn't hear what you gotta say. Yeah.
No.
No, okay. How many more classes are there? So Suriana, so basically I think we're going to be having a class next week, and I think one in August. There's going to be, I think, about 2 to 3 more classes, okay? So please, guys, keep submitting questions. If you see something in science that you're wondering about or that you're curious about, please send me the question because we'll answer and we'll kind of do something fun to help understand it more, all right? But hey, guys, everyone, thank you so much for attending, and I'll see you next week. We're going to have another class, all right? Bye.